So the next question is, can the sun shine by release of gravitational binding energy as it was thought in the 19th century? Let's see what would be happening. For the sun to release gravitational binding energy, that means that it had to be contracting. So the idea was that the sun was constantly decreasing in radius, and this decreasing in radius was then releasing gravitational binding energy. Let's see how that plays out. For that, consider the Virio Theorem. So the Virio Theorem states that twice the kinetic energy plus the gravitational potential energy is equal to the second derivative of the inertial moment, actually half of it. But let's assume that the contraction, if it's happening, is sufficiently small so that we can set here the right-hand side to 0. That leads to the more familiar form of the Virule Theorem, that twice the kinetic energy plus the gravitational potential energy is equal to 0. So according to this form of the Virule Theorem, the total energy must be half of the gravitational potential energy. Right? If you consider the total energy to be E, which is equal to the kinetic plus the potential energy, and from the Virule Theorem, then you substitute the kinetic energy to be the potential energy over 2, then this becomes simply the gravitational potential energy over 2. Now, I'm going to write this in terms of modulus because the gravitational potential energy is negative. So to keep track of what is negative and what is positive, let's write this in terms of minus the modulus of the gravitational potential energy over 2, so that the total energy is negative, the system is bound. So as a star steadily contracts, it becomes more gravitationally bound, making the gravitational potential energy W larger. And it follows then from this that the kinetic energy also has to become larger so that the star becomes hotter. But hotter by how much? Okay, suppose that the contracting star is increasing its boundedness by dW. That is, you pass from R to R plus dr. Therefore, you pass the gravitational potential energy from W to omega plus dW. Therefore, the kinetic energy also passes from the kinetic energy plus dk, the kinetic energy. Actually, let's do it finite differences instead of infinitesimal differences. So let's carry on these results. Let's carry on these basic considerations. So according to the Virio Theorem, so this is before the contraction and after the contraction. Now, according to the Virio Theorem, after the contraction, you have that the new kinetic energy, twice k plus delta k, plus the new gravitational potential energy, must be equal to 0. So you have what? Twice the kinetic energy plus the old gravitational potential energy plus twice the variation in kinetic energy plus the variation in gravitational potential energy is equal to 0. But from the Virio theorem from before, you know that 2k plus w is equal to 0, so that cancels out. So what this result is saying is that the amount of kinetic energy that was added is equal to minus half of the gravitational potential energy that was added. Again, let's put the modulus so that we keep track of what is positive and what is negative. Kinetic energy is, of course, positive. Now, the energy must be conserved. So let's apply the conservation of energy here. The new energy of the star is equal to the kinetic energy that it has now, k plus delta k, plus the gravitational potential energy that it had, plus what was added of kinetic energy. Again, group together kinetic and potential as the previous energy of the star, and now you add the kinetic energy plus the gravitational potential energy. Because the kinetic energy is equal to minus half of the increasing gravitational potential energy, you can write this in terms of the original energy plus half of the gain in gravitational potential energy. Well, let's keep track again here of the quantities that are positive. So this is an energy loss. Now this result is very intriguing. As the star contracts, it settles into a state of energy that is smaller than the energy that it had before. But energy must be conserved. The star decreases its energy by an amount delta E that is half of the gain gravitational potential energy. So this is a very puzzling result if the energy is conserved. The star decreased its energy upon contraction. And where did this energy go? So where is the other half? And the answer to that is radiation. It must have left the system as radiation. So this is a very elegant result. As a star contracts, half of the energy removed from the gravitational field remains in the system as kinetic energy, and half is radiated away. Gravitational contraction leads to release of radiation. In fact, Lord Kelvin suggested that this is how stars shine. The sun had started from a larger radius than it has now in a colder temperature, a cooler temperature, and has been decreasing in radius ever since and then heating up due to this increase in kinetic energy, which is increasing the temperature. They calculated for the values known for the sun. How much energy, how much gravitational potential energy does the sun have? For the sun, you have that the energy is about G square over R of the sun. That gives you about 3.8 times 10 to the 48 erg. So if you divide this by the solar luminosity, you should get a time scale, a radiative time scale for gravitational contraction. And the luminosity of the sun is also about 3.8 times 10 to the 33. Well, it's the same numerical factor. Of course, the order of magnitude is different, but close enough. Cut the numerical factor. It gives you about 10 to the 15 seconds, which is about 10 to the 7 years. 1 year is 3.1 times 10 to the 7 seconds. So that means that the time scale, like Kelvin Helmholtz, is about 10 to the 7 years. So 10 million years. Well, this cannot be the whole story, right? We know of rocks on Earth that are significantly older than that, but they didn't know that in the 19th century. And this was the best that they had. If you don't know about nuclear fusion, you have a very accepted theory of thermodynamics, and you have Newtonian gravity, and combined, they find a means for the sun to radiate and shine, and that gives you an age of 10 million years. This was the accepted age of the Earth in the 19th century. Kelvin died thinking that this was the age of the sun, and therefore the age of the Earth. The Earth couldn't be older than that. Again, this is not the accepted theory for the sun, but it is a significant source of energy for other astrophysical objects. Indeed, the release of gravitational potential energy is what powers quasars and active galactic nuclei. Indeed, the standard theory of black hole accretion shows by simple order of magnitude estimates that a black hole of about 10 to the 8 solar masses, accreting at a rate of 1 solar mass per year, will radiate at the rate of 10 to the 47 solar luminosities, thus explaining why quasars are seen all the way across the universe.